All right, in this video we are going to talk about molecular orbital theory. Okay, so in the last videos we were talking about hybrids, sp3, sp2, and sp hybrids. Those were atomic orbitals. Now we're going to talk about molecular orbitals. So this is a branch of quantum mechanics where basically we take all the orbitals for an atom or for a molecule and we combine them, and the orbitals no longer belong to an individual atom, they belong to the molecule. That might be a minor point, but it makes a big difference in what we see in terms of how the bonding looks. Okay, that may not have been the most elegant way to put that, but anyway, a couple of things I want to mention first. One is paramagnetism. Okay, you guys are all familiar with refrigerator magnets. Those are called ferromagnets. But there are different types of magnetism. And paramagnetism is the attraction of a molecule to a magnetic field. And this is much, much weaker than ferromagnetism, but it's really important. And the reason it's important for us right now is because it is due to unpaired electrons. Okay. So I'm going to link a video where I show, or where the video shows nitrogen being poured between a magnet and then liquid oxygen being poured between a magnet. The liquid nitrogen does not stick, but the oxygen does stick. And if we look at the Lewis structure for oxygen, for O2, here it is, there are no unpaired electrons. But because that oxygen does stick to that magnet, we know there have to be unpaired electrons. So molecular orbital theory will give us a picture of the bonding in oxygen with unpaired electrons, and it will allow us to explain the paramagnetism. The opposite of paramagnetism is diamagnetism. Okay, this is a repulsion of a molecule from a magnetic field. And again, very weak. And like I said, it's the opposite, so this is due to only paired electrons. So all the electrons are paired in this case. All right. Let me get my screen back under control. So, again, this is going to get kind of weird because not only do we have bonding orbitals, but we have anti-bonding orbitals. So a bonding orbital would look something like this. If we have hydrogen and hydrogen, this is just a kind of a pictorial diagram of what it looks like. Here's a bonding orbital for H2. Okay, that would be bonding. And let me show you just what an anti-bonding orbital would look like. And really, if you remember back to when we talked about orbitals in quantum mechanics, it's kind of similar. So they're different colors indicating different phases. And what we have in between them is a node. Okay, and at the node there can be no electrons, just like a node was previously. We more typically say there's no electron density or no electron probability being there, but you get the idea. And this is what we call an anti-bonding bonding. Molecular orbital. These are both molecular orbitals. Okay. So the idea behind a bonding and anti-bonding is the anti-bonding cancel out the bonding orbitals, and we'll see that in a minute. Okay, but if you have bonding orbitals and anti-bonding orbitals in equal amounts, they will cancel each other out, and you don't get a bond. Okay. There's also such a thing as a non-bonding orbital, but we're not going to talk about that. Okay. So let me just go through a diagram for hydrogen, H2. Okay. So the way this works, and you want to do it just the way I do it, because it is complicated enough as it is without making it up as you go. We're going to write, I'm going to just do valence electrons for the two atoms we're interested in. Okay, so this is hydrogen, this is the other hydrogen. In the middle, we'll have the molecule for hydrogen. Okay, and so what we get is a sigma 1s. Remember, sigma is a bond along the axis. And then we get a sigma star 1s orbital. Okay. And then usually what we do is we kind of just connect the dots just to say, well, the sigma 1s and the sigma star 1s, they came from the 1s orbitals of the hydrogens. Now, I know you're sitting there going, what in the heck is a 1s orbital? You're probably saying something different, like what the hell is a 1s orbital, or a sigma 1s orbital? This is a bonding orbital, and it is a bonding molecular orbital. Okay, so what does that mean? This is the anti-bonding molecular orbital. Now you say, okay, they're in equal amounts there. Well, notice we haven't put in electrons, so the electrons make all the difference. What we're going to do is we're going to fill in our electrons for our atoms, okay? And hydrogen, each hydrogen only has one electron. Notice that the bonding orbital is lower in energy. Like I said, draw it exactly as I draw it. There's diagrams in the book if you need a better drawing. I understand. But we put one electron in each hydrogen, and then those electrons, that just helps us count how many electrons we have. Those electrons fill up the molecular orbitals in order starting at the lowest energy level possible. Okay? So, there's one more thing we need to talk about. Well, first off, let's just answer a question right now. Is this paramagnetic or diamagnetic? So we're only looking at the H2 molecule. Okay? Is it paramagnetic or diamagnetic? Well, this is diamagnetic. And it is diamagnetic because we only have we only have paired electrons in the molecule. Remember, off to the left and right, those are the lone atoms before they bonded. In the middle, that is the molecule. One other thing we need to talk about is bond order. I'm going to put it down below so I don't run out of room. Bond order. Okay, and bond order is equal to bonding electrons minus anti-bonding electrons, all divided by 2. It's really a simple concept. I don't even use that equation. What I like to do is I like to look at the diagram and I say, okay, how many bonding electrons do I have? I have 1, I have 2. And do I have any anti-bonding? No, there's no anti-bonding up there. Okay, so I have 2 bonding electrons. 2 electrons make a bond, so my bond order is 1. Or if we want to use the equation, we say bonding electrons 2 minus anti-bonding electrons 0 divided by 2, and that is equal to 1. So that is a bond order of 1. What does that mean, a bond order? Well, it's just a different way of saying, is it a single bond, is it a double bond? That just means it's a single bond. All right, next video we're going to move on to helium.